By the middle of the 21st century, a team of fully autonomous humanoid robot soccer players shall win a soccer game, complying with the official rules of FIFA, against the winner of the most recent World Cup.
Robin, whose legs are fresh, Ramos' arms, Robin's trying to go around him. Still a chance for Arjen Robin. It's 5! It's a landslide!
Hi, my name is David.
Hi, my name's Ding.
Hi, I'm Caleb.
Hi, I'm Richard.
The goal of this project was to design a local vision soccer robot that could function under the rules and regulations of the small-size F180 Robo Cup League. The focus was to score as many goals as possible in the span of 5 minutes, all whilst avoiding other obstacles on the field. The main intention for the overall robot design was to provide an early platform for rapid prototyping for the navigational, drive and vision systems. Early on in the project, the team recognized that the robot required a sturdy but lightweight chassis to accommodate for the phone, electronics, kicker, and drive system. In optimizing the performance of robot movement, components were kept low and close to the center of gravity to allow quicker stop, start, and rotational movements. Along with the chassis, the kicker was designed to be simple, robust, and as cheap as possible, whilst meeting design specifications, as the team agreed that its performance was of a low priority compared to the functionalities of the other subsystems.
After receiving a camera frame from the phone, the frame was thresholded in the HSV color space to segment the desired objects into a binary image. The HSV color space allowed the effect of lighting to be disregarded, as opposed to the standard RGB color space. Dilation and erosion were then applied to fill any holes in the required blobs and remove unwanted noise. A final area threshold was then applied, further removing any noise. This process worked well to segment the ball, goals and wall, but the HSV threshold for close and far obstacles was not consistent. As a result, 2 separate thresholded images were generated for the far and close obstacles. These 2 images were bitmap orbed together to generate a single thresholded image for all obstacles. Using these processes, the remaining blobs in thresholded frames were then analysed to detect the X and Y location and width and height. This information was then passed to the navigation system.
The purpose of a navigation system is to take data from the vision system and determine where the robot should be moving. The program takes this information and determines what objective the robot should currently be moving towards. For example, if the robot can see the ball but hasn't acquired it, the robot will move towards the ball. Or if the robot has captured the ball, it will move towards the goal, while maintaining control of the ball. While doing this, the robot has to avoid obstacles and other players. To accomplish moving towards a goal while avoiding these obstacles, the navigation system performs what is known as a potential field analysis. The aim of a potential field analysis is to simulate an attractive force coming from the robot's current objective and simulate repulsive forces coming from the obstacles, players, and walls. The robot's current objective will pull it closer, while obstacles will push it away. The robot will use this information to choose an optimal direction to move. Once this potential field process is complete, the robot will have a direction to move and an idea of how badly it needs to move in that direction. The system will then determine what power and direction each motor has to run at, before sending this information to the microcontroller for use by the drive system.
The drive system that was chosen for this project was the differential drive system, due to its simplicity and the team members' familiarity with similar systems. A differential drive system utilises wheels on either side of the robot's body. It can change direction by varying the relative rates of rotation of each wheel. In Team 4's robot, this is done by varying the pulse width modulated signal sent from the phone to the microcontroller via Bluetooth. These commands are then passed into which direction each motor should turn and the relative rate of rotation of each motor. The robot needs to move in certain ways depending on which phase it's in. If searching for the ball, it's preferable that the wheels move in opposite directions, causing the robot to pivot about its axis and negating any possibility of running into obstacles. Contrarily, when the ball is in the robot's possession, both motors must turn in the same direction, otherwise it will lose it. By integrating all of this, the robot is able to find the ball, drive to the ball, drive the ball to the goal, and score.